Right. I think we'll get started, and I'll admit more people as they join the waiting room. So for the audience, thank you so much for joining. We've got the pleasure of having Dan Raper with us today from IBM, and he works as a software developer in the IBM MQ ZOS team. So it's going to be a nice introduction for us, and feel free to please add your questions into the chat. And I will put the feedback QR kind of link into the chat as well for you to access there also. So for now, Dan, I'll hand over to you, and please wow us with your slide deck and your information.
Thank you. So as you already said, I'm Dan. I work in the service part of the IBM MQ for ZOS team, mainly focusing on fixing issues that come up in our long-term support releases, which our customers are generally running on. So just to give you a bit of an idea of what's going to go on in this presentation. So I'm just going to start off with a high-level overview of messaging, and then go into the fundamentals of MQ, what it does for businesses, and some of the more advanced features. So first of all, it's worth acknowledging what we mean when we talk about enterprise messaging. So we're not talking about any sort of messaging between people, between different messaging services. We're talking about the encapsulation and the moving of data between different systems and applications running in your business, whether or not they're on a mainframe, on a server, on a client device, and regardless of what protocols they might be using. So an example could be an ATM talking to a bank. It could be a GPS tracker talking to a server. It's the machine-to-machine communications. So the first question we hear quite often is, why use messaging? So messaging solutions connect your applications asynchronously, and they simplify your application development as they give you one less thing to worry about when you're developing. You can focus on your business logic, and it breaks the tight coupling between applications. And I'll go into that a bit more in a second. So your applications don't have to know about each other directly, and they don't actually have to be available at the same time. So as a simple example, if you have two applications running, a producer and a consumer, the communication between these two is fairly straightforward. Whether you're using HTTP, whether you're using file, whether you're using TCP, the communications is fairly easy to maintain. But what happens when you start to add more applications? So you can already see this is about to be a bit of a nightmare. So you've got potentially quite a lot of links between these applications, and as an administrator, that's up to you to manage each of these links. So application one needs to know about all three applications. What if there's an outage? You have to handle all of this yourself. So we refer to this as a tight coupled or synchronous communication. So app A is always waiting on app B. If app A or B go down, they can't function independently, as they're waiting on they're either requesting or they're waiting for a response from the other application. So what if B needs to scale up? Well, A is still waiting every time it sends a request to B, and B is always waiting on A. If A is being too slow, B is going to be sat doing nothing. So as I already mentioned, the number of links between applications, so it goes up with the square of the number of systems. So every time you add another application to a system, another node, your number of connections is going up and will rise exponentially, which is a bit of an administrative overhead. And it means you can't react to external factors as easily. You can't scale up your application if you have to manage the scaling and the connections between every single part of your application. It's a lot harder to scale up if you, for example, if you're a retailer and it's a Black Friday sale, or you have a surprise sale, or a product is in higher demand. You can't scale to it as easily, and it could cause it could lose a competitive advantage and cause potential financial difficulties for a business or financial impact. So at this point, I'm just going to introduce two main concepts of messaging. So generally, we talk about message queuing, which is what the MQ and IBM MQ stands for, and event streaming. So message queuing, the messages represent some processing that needs to happen. So the example I showed in the previous slide, that will be an example of message queuing. You're sending a message, you need to process that message and potentially get a response. So for this, assured delivery is really important. So for example, a credit card transaction, the transaction getting there, the money being processed is very important. And so if the message doesn't get there, then potentially money is being missed on either side. In contrast to this, you have event streaming. So this is more state messages. So this is going to be, for example, a message from a temperature sensor or a measurement of some kind in an industrial process. The idea is that the messages, although are still important, if a message goes missing, it's slightly less impact to your business, and often you have a stream history. So you'll be able to go back and look with a lot of event streaming solutions. You'll be able to go back and look at what the temperature measurements were previously and how the stream has changed. So how does messaging solve the problem that I explained? So instead of application A and B talking directly, you have a queue in between the two applications. So instead of talking to application B, application A is not aware of application B. It puts a message on a queue to be processed, and B picks a message off the queue and processes it. So this is what we call a store and forward approach. So as the name suggests, it goes onto the queue and it's forwarded, B picks it up. So the advantages to this are that while in the synchronous communication example, A is sending to B, B is sending back to A, we can scale this up quite easily. We can have 5 instances of application A and they'll all be put into the queue, and we can have 10 instances of application B and they'll all be getting from the queue. And it means that instead of having to implement that logic into our application, all we have to do is point A at the queue and point B at the queue. So with message queuing, generally the messaging is point to point. So effectively, one message producer creates a message and it's consumed by exactly one consumer. So the producer puts message on the queue and the consumers pick them off the queue. So you can have as many consumers as you want and as many producers as you want, but the message only goes to one destination. So if a response is needed, you would handle this exactly the same way. You just have a request queue and you have a response queue. So it just goes both ways, and equally, one instance of it, A could send one message onto the queue, B picks it up, and then another instance of A picks it up on the way back. It doesn't have to be the exact same nodes. It can be scaled independently. And because of this, it means that both nodes, there's no need to be idle. A can make a stack of work for B to do, B can make a stack of work for A to do, and they can operate fairly independently. And as well, if there's a blip in the network, if there's an outage at any point in the chain, it's all just handled in that there's no direct dependence on any other component. So switching over to events, so the information is no longer distributed on a one-to-one basis. So as the slide says, think about sensor data or stock prices. There's not just one consumer of a stock price. It could be potentially millions of stock traders. It could be lots of different computer systems. And on the other side of this, business events, such as a purchase. There could potentially be multiple different departments that need to know when a purchase is made. You could have your logistics department, your accounts department. There's various different parties involved. So the model when talking about events is generally publish and subscribe. So instead of having a queue here, we have what's called a topic. So the message producer puts a message onto a topic, and consumers can create a subscription. So that can be to either one topic, or it can be to most solutions support a wildcard, and the same message goes to each subscription and in turn to the consumer. So instead of the producer producing one message, it going to one consumer, this time the message goes to all consumers that are subscribed to that topic. So in a normal publish and subscribe situation, if a consumer goes offline, any messages that are published to the topic in that time would be lost, as they're not seen as important. But a lot of solutions, including MQ, also have a durable publish and subscribe model. So with this, you have this distinction between durable and non-durable clients. And in this case, the durable client, when it comes back online, it will receive the messages. So it's very dependent on the needs of the business and the needs of the specific application as to whether or not you need this. And there's some more redundancy features that I'll talk later on in the slides as to a lot of the features that I'll bring up will very much depend on the importance of the message. And of course, that's up to the business as to how important, whether it's a credit card transaction or a bit of sensor data, how important that is and the impact to a message being lost. So while I'm mainly going to be talking about IBM MQ, there's also a event streaming solution called IBM Event Streams that can operate alongside MQ. So this is going to focus more on the publish and subscribe model, whereas MQ generally our customers are using it with point-to-point messages where assured delivery is really important. So I'm just going to now start talking about how IBM MQ in particular, what benefit it adds to messaging and what it does for our customers. So MQ has been around for a number of years now. So it started off in the early 90s as MQ series and was WebSphere MQ for a while, and is now IBM MQ. So despite being a mature product, as you can see, features have been added quite frequently in order to keep up with industry trends. So in recent years, we've added container support, we've added more high availability features, and always kind of tried to keep up with the market as much as possible. So our latest long-term support release was released last year, which is what our customers generally run on. And we also have a CD, a continuous delivery release that's released every few months, which is actually more bleeding edge features. So some of our customers will test those out in their test or development environments, but generally won't run them in production environments. So the four main reasons why businesses trust MQ are, first of all, reliability. So the assured delivery, that a message is delivered once and only once. So a message not being delivered could be detrimental to a business, but at the same time, a message being delivered more than once could also. For example, a bank transfer, if that's processed twice, you've effectively got inconsistent states between two bank accounts, or money missing, or double payments. So second aspect is scalability. So the idea with an MQ deployment is that it's very easily scalable. through features such as clustering that I'll go into a bit more detail in later. It's very ubiquitous, so we support a lot of different platforms, both for clients and servers, and I'll go into a bit more on the specifics later. And then security. So we offer fine-grained access controls, authorization, and as well as end-to-end encryption for when that is required. So just to introduce some key terms. So an application is what connects to MQ. So this could be a off-the-shelf solution or an internal bit of software. So these use our MQ libraries to talk to a queue manager. So a queue manager is the instance of MQ. And on a queue manager, we have queues, which are simply just a named resource, which is first in, first out generally, although there are multiple different retrieval methods. And messages sit on these queues. So messages are just chunks of data effectively. So a message can be in any format that you like. The application has to understand the format of the message if it's picking it off a queue, but it could be just arbitrary binary data, it could be JSON, it could be anything. And MQ offers features that can handle character set and content type decoding between different systems. And then we have the concept of channels, which are a way for one queue manager to connect to another queue manager. So if you put a message on a queue on one queue manager, it could go across to a queue on another queue manager. And you can either configure these manually, so you can set up a sender on one queue manager and a receiver on another, or these can be dynamically created using clustering features, which there's a section on later on. So the traditional MQ architecture deployment is called the distributed architecture. So in this instance, a queue manager runs on each application server. So on this slide, the pink represents the applications running and the blues are representing the queue managers. So on each system where your applications are running, they talk into a queue manager and the queue manager talks to other queue managers, which in turn talk to other applications. So this is a very reliable solution, as it handles network failures and keeps queue manager local, but can have some downsides in relation to administrative overhead. So if you've got a lot of application servers, you're going to need a lot of queue managers. And while we can cluster these and do some things to avoid that, it's not always the preferred approach, although the preferred approach does change. So in contrast to this, we have the hub architecture. So in this approach, you have a set of queue managers and your applications running on different hosts. They could be the same host, but they don't necessarily have to be. Your applications talk to the queue managers and the queue managers are handled independently. So in recent years, this is gaining more popularity as you can scale the queue managers independently. So an application doesn't necessarily have to connect to the queue manager running locally. It can connect to effectively any queue manager in a cluster, and the communications can be handled this way. So while this has its advantages, it also has its disadvantages. So rather than on the previous approach, you would have one application or one type application talking to each queue manager. In this approach, a misbehaving application could potentially take down a queue manager that's used by multiple applications. But being able to scale the queue managers independently is generally seen as a benefit, especially when you're using modern technologies like containers, which make it very easy to. So I mentioned channels. So a channel relationship, if you're going to define it individually or manually, it has to be defined on both ends. So you have a sender channel on one queue manager and a receiver on another. And a channel is effectively just a TCP communication between two queue managers. So anywhere a network connection can be formed between the two, you can have a channel. However, the general better way to do this is having an MQ cluster. So by adding a queue manager to a cluster, instead of having to manually create those relationships between two queue managers, the channels are defined automatically. And there's flexibility to this in that you can choose which resources are clustered, which resources are only specific to that queue manager. But when you're scaling up, it can help because you don't necessarily need channels to be created ahead of time. They can just be created dynamically. So I've talked a lot about how MQ runs, how it's architected, but the main concern for most users is, how do I connect my applications to a queue manager? So we offer a lot of different ways to communicate with them through various open source tooling, through MQTT, which we support through MQ telemetry, as well as the MQI, which is the MQ interface, which is our proprietary interface. And we now also support a REST API. So starting off with MQI. So MQI is the traditional way to access MQ, and we offer bindings in languages including C, COBOL, Java, and this provides access to MQ's full capabilities. So this is something we ship alongside MQ, and applications can effectively access the whole feature set. The second main way that applications talk with MQ is using JMS, which is now part of the Jakarta EE specification. So this is supported by standalone Java applications and in application servers, so WebSphere, Liberty, and WebLogic. And it simplifies the experience for a Java programmer, as you don't need any specific MQ knowledge. As JMS supports different messaging providers, it makes it a bit more of a provider agnostic approach. So MQ telemetry with MQTT allows MQTT clients to connect into MQ. So MQTT libraries are available for a lot of programming languages. It's generally more used in IoT applications and focuses on allowing client mobility. So for example, a GPS tracker, various mobile devices. And this is a OASIS and ISO standard. There are libraries available for C, C++, JavaScript, most ones you can think of. So we also support a REST API. So this can be used for point-to-point messaging and pub/sub, and just enables you to use post, delete, standard REST methods to interact with the queue manager. So this is ideal for REST native environments like JavaScript, but certain features are lacking from REST. So for example, if you're using the MQI or JMS clients, the assured delivery the assured delivery works a lot better, in that with HTTP, if you send off the request, you don't necessarily know how far it's got if the network's interrupted in between. Whereas if we're running something like a transaction, we can be sure with an MQI client whether or not the message has got there or not, and make sure that the whole transaction has succeeded. So something else that's seeing more popularity recently is the open source tooling. So we provide Node.js and Golang MQI libraries, and there's also a community maintained library for Python, which is a wrapper around the C library. And we also support a .NET Core MQ API, which is supported on both Linux and Windows. So the benefit to using MQ with your applications and with all these different APIs is that it doesn't matter which method you use to connect your application to a queue manager, they can all interact with each other. Whether or not if you put the message onto a queue from a C client, you can pick it up with an MQTT client or a JMS client or a REST client. MQ facilitates the interoperability between all your applications by sitting in the middle and allowing all these different methods to get and put messages. So I'll provide a link at the end of the presentation, but if you want some more information on messaging APIs, we offer a free IBM MQ Developer Essentials badge that you can study on the IBM Developer website. So I've mentioned the assured delivery and the fact that one of the big selling points with MQ is once and only once delivery. So there's a couple of ways that we can handle this. So message persistence. So when you define a queue in MQ, you can define whether or not the messages should be persistent or non-persistent. So a persistent message, as soon as it's put onto a queue, it's stored to a disk. And this means that if there's a failure in the queue manager, if it crashes, if there's a power cut, as soon as the queue manager comes back up, again, configurable, the messages can be recovered. In contrast to this, you have non-persistent messages, which are only kept in memory. So this is quicker, as you don't have to write to a disk. But if the power goes, if there's a failure with the queue manager, the message is going to be lost. So it depends on the nature of the message as to whether or not that's important. And as well as that, we support transactions. So just like with a database, multiple messaging operations can be combined and coordinated as one transaction. So just to give a quick example of transactional messaging. So if a consumer takes a message off the request queue, and then the consumer either fails to process that message or there's a break in communication, that message can go back on the queue for another consumer to pick up, or for that consumer to pick up once it recovers. So this ensures that just because someone's taken a message off a queue doesn't necessarily mean that we can't just straight away assume that the processing has been complete, especially as we haven't received a reply back for it. So where can you run MQ? So MQ can be run on-premise. We offer a physical MQ appliance, and MQ can be run in the cloud, either by yourself in a public or private cloud, in a Docker container, in OpenShift, in AWS, in Azure. So it can either be run by yourself in the cloud, or we offer IBM MQ as a service. So with the cloud offering, generally it's sold by the hour, like most cloud offerings are, and it's all the administration and everything, the patching, the basic maintenance is all handled by IBM, and the messaging aspects like the queues, topics, channels, connections are all handled by the user. So it takes away some of the admin overhead that you traditionally have with an MQ deployment. So we also, as I mentioned earlier, offer MQ in containers. So this can be used with alongside our cloud offerings, and is quite often used with Red Hat OpenShift, as it allows you to scale up your applications quite easily by just running it in a container. And the containers are fairly lightweight in that they can while they're idle, they're not really using much resources. And these can all be clustered together. So they operate as, they will interoperate as soon as you scale them up. So what security features does MQ offer? So throughout the lifetime of a message, there are many fine-grained access controls. So not only can we configure our key managers to authenticate a user, so to know who the user is and who they say they are, but also that the user has authorization to perform a certain action. So we can put access controls on different queues for different applications, for different users, which mean that it gives very fine-grained control to the administrator as to who can access what on your queue managers, and, for example, which queue managers can join a cluster. So depending on the platform it's running on, MQ offers quite a few different high availability features. So I'm going to get into a couple of these now. So the first thing I'm going to talk about is native HA. So this is a fairly new feature, and we basically maintain replicas of queue managers, and the messages persisted in 3 different locations. So this works quite well with cloud deployments, and there are no real external dependencies. The idea is that the queue manager and the messages are persisted in the event of a failure of any other queue manager. So on the other side, if you're operating on ZOS on the mainframe, we have the concept of shared queues. So all your queue managers host shared queues within a queue sharing group, and any application connected to any queue manager in the queue sharing group can consume a message from these shared queues. So it doesn't matter if you connect to queue manager A, B, C, D, you're still going to be able to get the same message off the queue. And if one queue manager fails, it's not a big deal in that the workload is recovered by the others, in that they can all access the same messages. So I've talked about how applications can put and get messages from a queue manager and MQ. I'm going to go into now about some of the administration and monitoring capabilities. So we offer 2 graphical interfaces to interact with MQ. MQ Explorer, which is a bit of Eclipse-based tooling, which can connect to your queue managers, can fetch messages, and is quite a useful administrative tool. And something that's a more recent addition is the web console, which is just a web-based way of performing some of the functionality that MQ Explorer provides. We also now have a REST API. So as well as a REST API to put and get messages from a queue, we also have a REST API to administer and manage your queue managers. And we also have our standard, more traditional methods of accessing MQ. So we have MQSC scripting, which you can either use as an interactive command line, or you can script it and run a bunch of commands at the same time. There's also a lot of third-party and open source tooling that can run with and interact with MQ. So there are a couple of features that are only available in MQ Advanced, which is a separately licensed version of MQ. So the first main feature of MQ Advanced is a message level protection, or AMS. So while MQ supports transport layer securities, TLS, on channels, so any communication with the queue manager is encrypted, we also have AMS. So AMS gives you end-to-end encryption on your messages. So when an application goes to, so it's completely application agnostic and it's policy based. So when your application goes to put a message to a queue, the MQ library will query the policy on the queue manager and encrypt it locally before it even leaves the application. So it's on the boundary between the application and the queue manager. And so this is depending on the deployment and depending on the messages, this can give you security benefits in that if your messages are sensitive, they'll be end-to-end encrypted, and you know that regardless of how many queue managers they go through, they're always going to be secure. So another feature of MQ Advanced is MFT, or Managed File Transfer. So this allows you to use your current MQ infrastructure as a way of transferring larger files. So yeah, it gives you all the same features that you have with MQ with your messages, and allows you to move larger files, which you wouldn't usually transfer as messages as such. And the final feature of MQ Advanced we'll talk about is FASP, which part of Aspera, which was an IBM acquisition. It accelerates the speed of a message transfer over long distances. So you can see from the graph, as the TCP latency increases, the message throughput decreases, which is something that FASP tries to solve, and is quite successful at. So when you've got long links across continents, when you've got the unreliable links, you could have queue managers operating on a train, in a moving vehicle. It allows you to still get a good throughput of messages. So that's all I've got to talk about today. If you want to learn any more about MQ, as I mentioned earlier, the link to the Learn MQ badge is on the screen. There's also documentation for MQ on the IBM Knowledge Center, and we have a YouTube playlist. So thank you. Are there any questions?
Thanks, Dan. That was really good. So there's no questions on the chat at the moment. So again, we invite our guests to put the questions in there if they've got anything at the moment. But first of all, thanks for keeping it simple for us today. I know it's a complex and highly powerful solution IBM have produced, but you've kept it very simple. And three key things I took away today is, first of all, tight coupling is the way applications used to run previously. So what's MQ's allowed us to do is to scale it, which is needed nowadays for the large-scale applications we're running. I really loved the publisher and subscriber model. That makes it really easy for us to understand. And also the concepts of durable and undurable messaging as well. So all these things people have to consider as they're building their MQ connections in their applications. So got a question actually in the chat. In your opinion, Dan, what are the main areas of improvement growth with IBM MQ? So perhaps what's on the roadmap? So
I think what is a definite persistent area for improvement and growth is introductions of and interactions with more with the current technologies that are being used. So a couple of years ago we introduced MQ for containers. So I think so far IBM's done a good job of keeping up with the industry trends, but I think that the main area for improvement is just maybe to keep keeping up with the industry, really. So we're now supporting more cloud providers and more high availability features, and these are the sort of things that customers are looking for. They're looking to see that they can interact it with their modern tooling.
Dan, can you hear me?
Yes, I can. I think you dropped out for a second.
I did, yes. I apologize for that. So yeah, let me just bring up the chat again. But essentially, we had a question around what would be areas for improvement for MQ going forward. Are you able to share any of that with us?
Yeah, so I think just keeping up with the latest industry trends, as we generally have done so far, and just being able to run wherever our customers need to, really, whatever new programming languages come in, whatever new technology like containers have done, like the cloud offerings have done, just keep up and run wherever our customers need it to, and then our customers will continue to be our customers.
Fantastic. And are you happy for anybody in the audience to contact you as well to maybe follow up with any further questions?
Yeah, of course. My details are on the GSE agenda. So yeah, if anyone has any more questions, feel free to reach out, and I can either provide you some more information or point you towards someone who can.
Fantastic. Thanks again there. So I don't see any more questions, but lots of thanks. So thanks again from me as well. And so if we can just leave this slide on for a while.
Yeah.
Anybody who hasn't given feedback, then please do either click on the link or scan the QR code and provide some valuable feedback. And Dan hopefully will be with us again for future occasions at GSE as well. So thanks once again.
Okay. Thanks for having me.
Let's just leave this up there for a second or so and then give people a chance. Okay. Brilliant. Okay, no more comments there. So we'll close the call there and hope to see you again soon, Dan.
Right, perfect. Thank you.
Take care. Bye-bye.